For more than 2 days, the room at the Johns Hopkins Applied Physics Laboratory was almost entirely silent. There was nothing to do, no telemetry to check, no commands to send, no signals to receive. Moving at over 430,000 miles per hour, a spacecraft about the size of a compact car was flying alone through the atmosphere of a star. It was December of 2024, and no one on Earth knew if it was still alive. When humanity finally tried to touch a star, to fly a machine inside its outer atmosphere and survive, this is what it looked like. A handful of engineers in a quiet room, waiting on a beacon that might never come. This is the story of how that machine was built, what it found inside the sun, and what came back. Most people assume the sun is dangerous simply because it's hot. The visible surface of the sun is about 10,000 degrees Fahrenheit, or roughly 5,500 degrees Celsius, hotter than anything you'll ever encounter in your life. But here's the part nobody tells you. The surface isn't the most dangerous place on the sun. The most dangerous place is the corona, the sun's outer atmosphere, a vast invisible envelope of plasma that extends millions of miles outward in every direction. And the corona is not just hot. It is between 1 and 3 million degrees Fahrenheit, up to 300 times hotter than the surface directly beneath it. That fact, on its face, should be impossible. When you walk away from a campfire, the air gets cooler. Heat falls off with distance. That's what we'd intuitively expect from everyday experience. Yet the sun does the exact opposite. Move away from its surface and into the corona, and the temperature explodes. For decades, scientists have called this the coronal heating problem, one of the most stubborn, unsolved mysteries in astrophysics. In 1958, a young astrophysicist named Eugene Parker published a paper arguing that the sun was constantly blowing out a stream of charged particles in every direction. He called it the solar wind. When he submitted the paper, the journal sent it back. The peer reviewer said it contradicted established physics and shouldn't be published. Parker appealed. The paper was published only after the editor-in-chief, a man named Subramanian Chandrasekhar, who would later win the Nobel Prize, personally intervened. 2 years later, spacecraft measurements confirmed Parker had been completely right. He became one of the most important figures in solar science of the 20th century. So when NASA finally started building a spacecraft that would dive into the sun's atmosphere, they decided to do something they had never done before in the agency's entire history. They named it after a living person. Parker was 91 years old when he stood on the launch pad in Florida in 2018 and watched his namesake rocket into the sky. He died 4 years later, at 94, having lived just long enough to see the spacecraft begin to transform our understanding of the star he had spent his life trying to explain. And now imagine being the engineer responsible for actually building this thing. How do you make a spacecraft that can survive inside a star? The heat shield experiences temperatures approaching 2,500 degrees Fahrenheit during its closest passes. Hotter than lava. Hot enough to melt steel, aluminum, titanium, almost any metal you can name. And yet the instruments behind the shield operate at roughly room temperature. The trick is a single piece of material about 4.5 inches thick. A heat shield made of carbon-carbon composite sandwiching a core of carbon foam, 97% air. The sun-facing side is coated in a special white ceramic paint that reflects most incoming sunlight rather than absorbing it. But here's the part that surprises people most. The corona is over 1 million degrees. Why doesn't the spacecraft just vaporize the moment it enters? Because temperature and heat are not the same thing. Temperature describes how fast individual particles are moving. Heat describes how much energy those particles actually deliver when they collide with something. The corona is shockingly hot, but it is also very nearly a vacuum. There are so few particles in each cubic centimeter that even though each one is racing at extreme energies, the total heat delivered to the heat shield stays manageable. 1,000,000 degrees in a near vacuum. Combined with the corona's extremely low density, the heat shield can survive those conditions. After launch in August of 2018, Parker's solar probe didn't fly directly toward the Sun. It couldn't. The solar system's geometry makes a direct approach almost impossible. A spacecraft launched from Earth carries too much orbital velocity and would remain in orbit around the Sun unless it somehow shed a tremendous amount of that velocity. So instead, NASA used Venus as a brake. Over the next 6 years, Parker's solar probe flew past Venus 7 times, each pass using the planet's gravity to bleed away orbital speed and pull the probe's path tighter and tighter around the Sun, like a fishing line being slowly reeled in. The final Venus flyby happened in November of 2024. After that, there was nothing left to do but wait for Christmas Eve. On December 24th, 2024, Parker's solar probe entered the closest pass any human-built object has ever made, only 3.8 million miles above the Sun's surface. For comparison, Mercury, the closest planet, never gets within 28 million miles of the Sun. Parker was more than 7 times closer to the Sun than the closest planet ever gets. And as it approached, solar interference made communication impossible during the closest approach. Communication went silent. No telemetry. No beacon. Nothing. For more than 2 days, the spacecraft flew on autopilot through the atmosphere of a star, unable to receive a single command, unable to send a single message, while a small team at Johns Hopkins sat at their consoles through Christmas Eve, through Christmas Day, and waited. On the evening of December 26, the beacon returned, a single tone. "I am here. I am operational." The room erupted. When the full data started downloading in early January 2025, scientists finally had something they had never had before: a view of the Sun's corona from inside. Parker captured unprecedented observations of the region where the solar wind forms and accelerates, streams of charged plasma pulling away from the Sun's surface and organizing themselves into the same wind that eventually reaches Earth and disturbs our magnetic field. It had filmed something called the solar wind U-turn, regions where solar material near the Sun reverses direction, pulled back by the Sun's own complex magnetic field. And it had captured the switchbacks, strange, zigzagging reversals in the Sun's magnetic field that scientists believe may help explain the coronal heating problem. 80 years of mystery may finally be cracking open. And the mission isn't over. Parker's solar probe is still in orbit, returning to its closest approach every few months. Each pass collects new data. Each pass refines what we know. Each pass takes us a little deeper into the star that our entire civilization quietly revolves around. Solar storms are not a hypothetical danger. A storm comparable to the 1859 Carrington event today could cripple satellites, knock out power grids across continents, and take months or years to recover from. Depending on the event, warning times can range from minutes to many hours before a major solar event reaches Earth. The data Parker's solar probe is collecting near the Sun, seeing how the solar wind forms, how coronal mass ejections actually behave at their source, could improve forecasting and potentially extend warning times for some events. That difference is not academic. That difference protects everything modern civilization runs on. For thousands of years, every culture that ever looked up at the Sun treated it as something untouchable. A god, a mystery, a force beyond human reach. On Christmas Eve of 2024, we reached anyway, and the star let us look.